Today we are going to start the discussion on unit number 3, the number system and logic gates. As per your university syllabus, the following topics are mentioned in the syllabus. Under number system, the binary number system, BCD, octal, decimal, hexadecimal number system and their conversion and arithmetic in this number system is to be discussed. The theorem, those are used in binary number systems called De Morgan's theorem, those are covered. Then our focus will be changed to digital electronic building blocks. Those are basic gates, AND gate, OR gate, NOT gates. Then we will study universal gate. Those are NAND gate and NOR gate. Then we will see some of the building blocks using basic gates and implementation like half adder and full adder. Then we will see the memory storage element like flip-flops. Under flip-flop, we will see SR flip-flop, JK flip-flop, T flip-flop, and D flip-flop, that data flip-flop. The last topic will be introduction to microprocessor and microcontroller. And here it is mentioned only block diagram and explanation. That is your syllabus of unit number 3. So let us start. We will start with some preliminaries. Let us see signals and systems. In electrical engineering, we will mostly focus on two signals, that is voltage and current. According to their representation, the signals are classified under two categories, analog signals and digital signals. The voltage and current signals are the functions of time. The analog signals, also called as continuous time signal, they are the function of t, like if it is a voltage, it is a function of t and it will be represented by infinite set of points. Means they plot a continuous trace of line. They can be repetitive or non-repetitive. The digital signals are also called as discrete time signals and they are represented by only finite set of points. Means they are defined at particular time only. Following figure shows the examples of digital signals and analog signals. See here in the figure 1, here it is a sinusoidal signal and it is a continuous time signal. And you will see that it traces a smooth line with respect to time. Means for every instance of time, there is corresponding value of the voltage. So this signal will be represented by infinite number of points and that's why it is continuous signal. The analog signal and digital signal can be repetitive or non-repetitive. Here in this figure, the sinusoidal signal is repetitive and it repeats with a specific time period. Whereas if you see the digital signal have only discrete values. For example, for certain duration, the value is 5 volt. Then the next duration it is 0. Again for the next interval, it is 5 volt. Again it is 0 volt for the next duration. Likewise. So total signal is repetitive, but it will be only represented by the discrete values. In the second figure, you will see again another type of analog signal. Again, analog signal need not be having constant amplitude. It can have any amplitude, only it will be represented by infinite number of points. So for every time instant, there is a corresponding value of the signal. This type of signals are called as analog signal. If you see the corresponding digital signal, the digital signal will be only defined by the few discrete values. For example, during this interval, first interval, the digital value is shown here. Whereas during second interval, the digital value is low, right? Whereas during the third interval, the digital value is change again. Likewise, only few values represents the digital signal. If you compare these two signals, their variations are similar, but here compared to analog signal, digital signal have many lost part. Some of the parts of the analog signals are lost while converting it to digital signal. The third figure again indicates another analog signal which is randomly varying with respect to time, but it is continuous signal. Whereas the digital signal shown here, which is having only two values, the high value and low value. By using only two values, the signal can be represented in this particular example. So by conclusion, we can say that analog signals are the set of infinite point signal, whereas digital signals are represented by a finite set of points. The digital signal representation. The type of digital signal can be represented by binary combinations. Number of distinct values are shown here. In binary, there are only two distinct values, 0 and 1. If the signal is represented by octal system, then there are number of distinct values are 8. If it is represented by hexadecimal system, then the number of distinct combinations are 16. Now let us see what is system or circuit. System is basically a group of interconnected component or physical devices or algorithm to perform the required operation on the applied input data or signal. There are two types of system generally classified in theory: analog circuits and digital circuits, or say analog systems and digital systems. The analog systems are the system which process the analog signals. They are having input as analog signals and the processed output, that is also the analog signal. The typical examples are filters, amplifiers, and signal generators, etc. The digital systems are also called discrete system. These system process the digital signal to produce the digital signal output. See in the block diagram, this is the digital system or circuit. Inputs are digital inputs. It can be single channel or multi-channel digital inputs or multiple digital signals, and it can generate single or multiple output digital signals. The typical examples are digital adders, subtractors, the data registers, the flip-flops, the counters, microprocessors, calculators, and computers, and so on. The binary logic and logic levels. In binary systems, there are two systems of logic representation: the positive logic system and negative logic system. In positive logic system, there are two symbols, logic 0 and logic 1. Logic 1 corresponds to true, that is in electrical circuit represented by 5 volt, and logic 0 that corresponds to false, and that is represented in actual electrical circuit by 0 volt. Whereas in negative logic system, the role of true and false will be reversed. The true means it is logic 1 and that is represented by 0 volt in the electric circuit, and false is logic 0 and that is represented by 5 volt in the corresponding binary electric circuit. It is shown in the figure here. See, in the negative logic system, 0 volt level is logic 1 here, and in positive logic system, 0 volt corresponds to logic 0. Whereas in positive logic system, 5 volt corresponds to logic 1. Whereas in negative logic system, 5 volt corresponds to logic 0. Most of the time, we are using positive logic system only. Let us focus on the study of number systems. Number system have two important components: the base of the number system, also called radix, and the weight of the system, that is also called as positional weight. The base of the system is nothing but the number of symbols used to represent the various positions of digit in the system. For example, in digital system, the number of symbols used are 0 to 9. Therefore, total number of symbols are 10, and thus the base of the system is 10. The largest digit in the decimal system is base minus 1, that is 10 minus 1. And this logic is applied to all forthcoming system. What is weight? Weight is basically a positional value of the digit. Let us see the example here. If this is a system, there is a point called radix point. Left hand side to the radix point is a integer portion, and to the right side of the radix point there is a fractional portion. So let us see the position here. Let us consider the position is numbered from 0. So 0th position is immediately to the left of the radix point, then first position, then second position, then third position, and so on. The position weight shown here is b raised to power 0. B stands for base of the system. B raised to power 1, B raised to power 2, and so on, increasing towards the left. For example, if base of the system is 10, means it is decimal system, then 0 position is 10 raised to 0. We are calling it unit position. The first position is b raised to 1, that is 10 raised to 1, means 10. The weight of first position is 10. Weight of second position is 10 raised to 2. Weight of third position is 10 raised to 3. And weight of fourth position is 10 raised to 4, and so on. That is in decimal system. So here the figure indicates a generalized diagram of any number system in which the integer part is the left part of the radix point, and the positions are from 0 position to n number of position. Those are increasing in left side. And the position weight will be the power of the base starting from 0. So the power go on increasing from 0 to n on left side for integer portion. If you see the fractional part, the right side of the radix point, then the position weight of the first position is given by b raised to minus 1, where b is the base again. Second position will be b raised to minus 2, third position will be b raised to minus 3, and so on. For example, if it is a decimal system, then base will be 10. So this first position will be 10 raised to minus 1, means 0.1. Second position will be 10 raised to minus 2, means 0.01. Third position weight will be 10 raised to minus 3, means 0.001, and so on. Let us see the example in the decimal system. If the number is 349.25, how it can be represented by the system? Whereas if you see the number representation here, the number will be put in the bracket and there is a subscript 10 mentioned. This is one way to represent that this number is a decimal system. Whereas in decimal system, we normally ignore this subscript. Sometimes instead of 10, the letter D can also be used. And in decimal system representation, most of the time, we simply ignore the subscript. We just say 349.25 is a decimal number. Now, if you see this number and its corresponding weight, see the integer portion left to the decimal point. Now, this radix point becomes the decimal point. The 0th position is 9, that is unit position. So, it will be, the digit will be multiplied by the weight of the position, that is 10 raised to 0. So, that corresponding total weight of this first position is 9 plus into 1, that is 9. The second digit is 4 and weight of the position is 10 raised to 1. So, therefore, the total weight of second position or this position is 4 into 10 raised to 1, that is 40. If you see the third digit is 3 and the position weight is 10 raised to power 2. So, therefore, that is 100. So, 3 into 100 is 300. So, therefore, position of or total weight of this digit 3 is 300. Add these all the weights, 300 plus 40 plus 9, that becomes 349. Whereas if you see the fractional portion, in the fractional portion we know the position weight is increasing with the negative power of base. Here base is 10. So the first digit after the decimal point on right hand side is 2. The positional value of this position is 10 raised to minus 1. So therefore, the value will be 2 by 10, that is 0.2. Whereas the next digit, 5, the position value is 10 raised to power minus 2. That is 5 by 100, means 0.05. And therefore, the total value will be addition of these individual position weights. And that comes out to be 0.25. This general fundamental will be applicable to any system further we are going to study. So if you remember this, you can easily understood the forthcoming systems. The various number systems, those are used in practice, are listed here with their base values. The binary systems have base value 2, means there are only 2 symbols to represent any number in binary. The octal number system have the base value of 8. The decimal number system have the base value of 10. The duodecimal system have the base value of 12. The hexadecimal system have the base value of 16. Means in hexadecimal system, the total number of symbol used to represent any number is 16. Out of this system, binary system, decimal system and hexadecimal systems are quite popular. Let us review the decimal systems to which we are very familiar. The system base is 10, means number of digit used are 0 to 9. The largest value of any digit will be 9. The position weight is multiple of power 10 as shown here. Let us see the radix point. The integer portion, we will see the 0th position, the position weight is 10 raised to 0, that is 1. The first position, the weight is 10 raised to 1. The second position, the weight is 10 raised to 2. The third position, the weight is 10 raised to 3, and so on. On the right side of the decimal point, it is the fractional portion. The fourth position have weight 10 raised to minus 1. The second position have weight 10 raised to minus 2. Third position have weight 10 raised to minus 3, and so on. Let us see the another number system, the binary number system. In binary number system, the system base is 2. Means there are only 2 digits to represent any number, 0 and 1. We can say logic 0 and logic 1. The largest value of the digit is logic 1. The position weight is the multiple of power of 2. Again, see the radix point. Here, radix point is now the binary point. The 0th position have the positional weight of 2 raised to 0. The first position have the positional weight of 2 raised to 1. The third position have, second position have the positional weight of 2 raised to 2, and so on. On the right side of the binary point, the first position have the weight of 2 raised to minus 1. Second position have weight 2 raised to minus 2, and so on. A typical example is shown here. Let us find out the equivalent decimal number corresponds to the binary number 1011.011. Whereas here the number in red is the integer portion and the number in blue color is a fractional part. So the binary value is written as it is here in the figure. Consider the binary point. The left side of the binary point is the integer portion. The 0th position have the weight 2 raised to 0. So the digit is 1 into 2 raised to 0. The positional value is therefore 1 into 2 raised to 0 is 1. The first position is 1 into 2 raised to 1. Therefore, the weight of this position digit is 2. Third digit is 0. So 0 into 2 raised to 2. And therefore, the total position value of this digit is 0. The third position digit is 1. And therefore, the weight is 2 raised to 3. So 1 into 2 raised to 3, that is 8. So we have individual positional weight 8, 0, 2, 1. Add the all position weights. You are getting the total integer portion. That is 8 plus 2, 10 plus 1, 11. So integer value will be 11 as shown here. Now let us convert the fractional portion. We know the first position to the right of the binary point, the position weight is 2 raised to minus 1. So 0 into 2 raised to minus 1 is 0. The second position is here shown by the digit logic 1. So 1 into 2 raised to power minus 2, that comes out to be 0.25. The third position is the least significant position. The digit is 1. So 1 into 2 raised to power minus 3, that comes out to be 0.125. Add all the individual position weights of the digit. So 0, 1, 1 binary corresponds to 3.75 decimal. So total number, therefore, 1011.011 in binary is corresponds to 11.375 in decimal. The binary numbers are represented in number of bits format. Here, bit defines the single position, whereas nibble defines the combination of 4 bits. Byte defines the combination of 8 bits, and word defines the combination of 16 bits. Likewise, double word defines 32 bit and quad word define the 62-bit representation of a binary number. A table here typically shows the representation. If you see the word representation, the binary value represented here by 16-bit, whereas in Nibble, each binary value will be represented by group of 4 bits. In bytes, each binary value will be represented by group of 8 bits. Let us see the another number system, octal number system. The name itself indicates that this system have base 8. Means this system have the total number of symbols 8. That is 0 to 7 digits. The largest value of the digit is 7. The position weight is the multiple of power of 8 as shown in the figure. So see the integer portion. The same logic we will apply here. The radix point is now called octal point. The 0th position have the weight 8 raised to 0. That is 8 raised to power 0. The first digit have the weight 8 raised to power 1. That is the position number. The second position have the weight 8 raised to 2. And third position have the weight 8 raised to 3 and so on. The fractional portion, that is to right of the octal point, the first position have the position weight of 8 raised to minus 1, that is actually 1 by 8. The second position have the positional value 8 raised to minus 2. And the third position have the power 8 raised to minus 3. The typical number system shown in the table here, it consists of only 7 digits, 0 to 7 digits, means 8 symbols. So the numbers are 0, 1, 2, 3, 4, 5, 6, 7. And after 7, the next digit will be 1, 0, then 1, 1, 1, 2, up to 1, 7. After 1, 7, the significant digit will be increased by 1. And least significant digit, the lowest digit will be reset to 0. So therefore, the next column, you will get the number 20 to 27. The third column, after 7 of least significant position made 0, and the most significant position of the column will be incremented by 1, that is 3. So 30 to 37. From 37, it will be 40 to 47 and so on. In decimal system, if you compare this, we are going from 0 to 9. After 9, it will be 10 to 19. Then after 19, it will be 20 to 29 and so on. So in every system, the logic is same. You have to only identify what is the base of the system and then accordingly find out the weight of the position, that is power of the base, and the total number size can be obtained by adding each positional weight, integer portion as well as decimal portion, and that represents the number in that system.